Let C be parameterized by the curve. So R of t is t comma t squared. So that says in the x coordinate you behave like t, in the y coordinate you behave like t squared. And time goes from 0 to 2. The question is, along this curve, what is the integral xy dx plus x squared dy? And the options were 4, 6, 8, 10, or 12. Did anybody work it out? Did everybody work it out? E, 12. Good. Now the nice thing is the integrals look high dimensional because you see both x's and y's, but it's a one-dimensional integral, and the way you remember that is you count the number of integral signs, and you're like 1. Okay, so that's one-dimensional integral. So what you're going to do is you always say, I'm going to get it down to a single parameter, unless there's a better way, which we'll talk about today. But for this one, there's not a better way. And what's the idea? Everywhere where you see x, replace it by your x of t. Everywhere you see y, replace it by y of t. Everywhere where you see a dx, you put your x prime of t. Everywhere you see a dy, you put your y prime of t. And you just update. And now you add your bounds, 0 to 2. Those are your bounds. And you have an integral. And you work it out, and you get 12. All right, so this one's not particularly bad. These are very easy functions. These are also very easy functions. You could imagine things can get worse, and that's what we're going to talk about. Any questions? Yes, I see a question.
So why didn't you do the thing where you take the derivative and then have like the square root of 1 plus 14 squared dc?
Okay, so there's a question where you might have thought about last time. Said, hey, didn't we talk about last time there's this integral along a curve of f of xy ds? And in that case, it's the integral from a to b, f of x of t, y of t, square root x prime squared, y prime squared dt. Where did this go? Now, to answer that, you have to think about what kind of integral we're doing here. So this integral, for lack of a better word, now I'm trying to get to the word orientation in a natural way. So I'm just going to say there's an orientation involved. This is an integral with an orientation, which is to say I start at time 0, I'm starting at 0, 0, and at time 2, I'm ending at 2, 4. So I'm ending up here at 2, 4. And I'm going in between. But I'm following this direction because, t is oriented. There's a time 0, there's a time 2. And so there's an orientation to your input, which becomes an orientation for the curve. And orientation matters in this type of integral. So this is an integral where we care. Now, on this type of integral, orientation does not matter. And so what's happened is when you've gone and switched from an integral where orientation doesn't matter to one where orientation does matter, it causes things to change. Now, you might say, like, what? How? Why is that? It doesn't look like this is an integral where orientation doesn't matter. Because if you think about, and I know that you often do while you're walking around, you start thinking, let me think about multivariable calculus problems. I find myself doing that quite a lot. And you can try it out. It might help. So if you think about what this is representing, it says just split your curve into pieces, and for each piece, the contribution is the value of the function, which you can think of as a density if you're looking for mass, or you can think of it as a height if you're looking for area. But it's the value of the function times a small length, and this length is a positive length. There's not a chance for s to be positive or negative. So ds is always non-negative. dx, dy could be negative. There's a sign attached to them depending upon how x is changing. So this particular curve, yes, it's true that x and y always went in the positive direction, but a different curve could have been traveled, would have given us a different answer, where x and y may have had positive places. X and y may have had, well, dx and dy could have been positive or negative. So there's two camps. Okay, so I'm gonna make a list here. Non-oriented camp. And in the non-oriented camp, you have no choice. If you see an integral that looks like this, you just got to grin and bear it. That's what you have to do. The oriented camp, there's several notations. The one we started out with, these are all just different notations. And as a fellow faculty member said, it's annoying that we give them so many different notations for the same thing. But you have f dot t ds, and here t is the tangent vector. So it's the, given your current place, what's the direction? So it's the unit tangent vector and then ds. So this t is giving you your orientation. This is the same as the integral along the curve f dot dr, where dr is your dx comma dy. And the one I like, just because it's easiest to apply the rules here, m dx plus n dy. Now, where did the square root go? The answer is it's actually inside of this t. Because if you think about t is a unit vector, and it's a tangent vector. So first off, just a tangent vector is x prime, y prime. When you normalize it, you divide by square root of x prime squared plus y prime squared. So there's a square root of x prime squared plus y prime squared in the denominator. There's a square root of x prime squared plus y prime squared in the numerator. They cancel out. So they go away. So these kinds of integrals, you are not going to have to deal with that square root term, which is why we prefer these types of integrals, and also because of what we're going to talk about today. That was a very long answer. I hope that's okay. Reasonable? Okay. Whew. Good. Other questions? All right. Well, today, our thought for the day. The greatest teacher failure is. I don't know if I can do a good order, but let's see. The greatest teacher failure is. Is that reasonably close? Okay. At some point in your life, you'd find out that the person who gave the voice to Yoda is the same person who gave the voice to Miss Piggy. And you're like, what? That doesn't seem right. But anyways, so yeah, oftentimes there's sort of these two things. One, we don't like to fail. It sucks. Excuse my language, I know I shouldn't swear, but it doesn't feel good. But at the same time, failing is oftentimes when we have an opportunity to learn. And so we try to avoid situations where we might fail. And I think that's not a good thing for us. If we want to grow, if we want to learn, we have to be willing to risk. We have to be willing to be wrong. And we learn from being wrong. We learn from being wrong not because it's like, as soon as you're wrong, you've learned. But you're like, oh, I wonder what I did. And you say, I see where my mistake was. Now I know not to do that. Let me try again. And so, don't be afraid of failure. It's not so bad. Be afraid of not wanting to try, I suppose, is the moral. All right, so what's the goal for today? We want to talk about line integrals, these one-dimensional integrals. But we finished last time by saying, by example, we said, well, sometimes when you have a curve, if you change the curve, but don't change the start and stop, you could get different answers. And that didn't feel right as far as fundamental theorem of calculus. Because fundamental theorem of calculus is sort of this feeling like, oh, there's something happening at the endpoints with some sort of antiderivative, and that gives us the whole answer. So we want to have that same thing happen again. And oh dear, I skipped the one. Where did that page go? All right. Well, so the punchline, and here's the punchline, I need to justify the punchline, is that the line integrals of conservative functions is easy. And that's what we're going to end up with. So let me jump back here, because I forgot to bring a page. All right. Suppose, for a moment, we are good at remembering things. It could happen. We could mess up and actually remember stuff. No, you have young, healthy brains. I believe in your ability to remember things. So the chain rule. Okay, chain rule, that sounds like something we learned. And we have a function f of xy, where x is a function of t, y is a function of t. And I can say, well, what happens? F depends on x and y. X depends on t, y depends on t. So I'm making a chart of all these variables here. Now, we mark the derivatives. Partial f, partial x, partial f, partial y, dx dt, dy dt. And the question, what if I want to take the derivative? So, in particular, the derivative with respect to t of f of x of t, y of t, would be what? Do you remember? Okay, so someone said, hey, I see a way to get to the t. Partial f, partial x, dx dt. Nice! So is that our answer? Well, I wrote it down, so maybe it's part of our answer. So if it's not our answer, what else? The other side, yeah, plus partial f, partial y, dy dt. Okay, cool. Nice. Well, okay. Well, what's that? Well, one way to think of this is your partial f, partial x, comma, partial f, partial y, dot, dx dt, dy dt. Okay. And now our great, something interesting is here. Partial f, partial x, partial f, partial y. We have a name for that. Gradient. It's a gradient of f. Dot. Now this, we've given it a name. It's dr. So, here we go. Suppose we have an integral along a curve, and let's say our curve is parameterized. We'll do it 2 dimensions, but it doesn't really matter, any number of dimensions. Same idea, where alpha less than or equal to t less than or equal to beta. All right, so then the integral along the curve of gradient of f dot dr. So that's the type of integral we were talking about, the type of oriented integral, but a special case where we are looking specifically at not just any type of function, but one which is conservative. So remember, if you take the gradient of something, we call that a conservative vector field or a conservative function. Okay, so we say let's put everything in terms of t. Well, according to this would become integral, use our bounds, alpha to beta of the derivative of f of x of t, y of t, dt. Because I'm just replacing. Now, the challenge. Is it possible to integrate a derivative of something? It is. What do you get? Yeah, you basically get this part. Now, is it technically that? No. But can we write it down? Yes. And if you're wondering, wait, what's the technicality? Well, technically within a constant, but because it's a definite integral, we don't care about the constant. So, evaluated from t equals alpha to t equals beta. All right. And lo and behold, what are we using here? The fundamental theorem of calculus. And that's sort of a theme here. There's going to be 3 times we talk about fundamental theorem of calculus, maybe 4. Let's say 4. Between now and the end of the semester, this is number 1. So this is a fundamental theorem of calculus result. Well, let's go a little bit further. This is f of, you have your x beta, y beta, subtract f x alpha, y alpha. But let's think about what these are. For instance, x beta, y beta, what is that in terms of the curve?
One of the endpoints?
It is one of the endpoints. Which endpoint is it? Is it the start or the end? It's the end, because you end at beta. We're using the orientation of t. So this is your end. What is the x alpha, y alpha? Start. So this is your potential function evaluated at the end, subtract the potential function evaluated at your start. Okay. Now, this feels better. Because what? Well, first thing is, does it matter how C got between the 2 points? So let's say this is our start, and over here is our end. And let me draw a curve. Here's a curve. I'll call this curve C1. Here's a different curve. Woo! I'll call it C2. If we have the integral of C1 versus the integral of C2, what will happen? Why will it be the same? They have the same start and end. So it turns out, if you are in this special case, as long as your curves start and end at the same point, you're going to get the same value. So this gives us, in particular, 2 strategies. So we're going to spell them out here. Now the first strategy is find your potential function. Why? Well, that says I'm integrating something. If it turns out it's a conservative function, if I find the potential function, I evaluate at the endpoints, life is good. Second strategy, BYOC. Bring your own curve. If you don't like the curve they give you, do a different curve, because it'll be the same. Now, that assumes you are conservative. If you're not conservative, you have to bite the bullet and do it the long way. Replace x by x of t, replace y by y of t, so forth and so on, and fill up the pages. All right, so that's today. Okay, so that was a page I forgot. I don't know what happened to that page. But continuing, the punchline, line integrals of conservative functions is easy. Well, maybe it's more accurate to say easier. There are still going to be some non-trivial things that happen. And so the punchline, this is what you should remember. If I'm integrating a conservative function, I take the potential function at the end, subtract the potential function at the start. So I'm using A and B to represent the start and end points. These are, of course, the same two approaches. All right, so let's do a problem. We're going to find the integral along the curve y dx plus x dy, where c is the following. We're going to start at 0, 0. We're going to end at 1, 1. And then we're going to take our time to get there. All right, so there's C. Now, if needed, we'll try to figure out a parameterization, but there's kind of a clue that is going to be built into these problems. If things look terrible, don't do it the direct way. Try to think of like, oh, is this something where I have a better method? Okay, so is there any hope for us? Oh, come on. Come on. I'm not that mean. I give a little bit of hope. Okay, so this is slightly different notation. So keep in mind that we are focusing on, when we have these pieces, what's in front of the x dx term. I'm going to think of this as y. What's in front of the dy term is x. So this is my vector field. And the question we ask ourselves is f conservative? In other words, can we find something that gets us, so we take the gradient of that function, we get capital F out. And we'll go through and be systematic about it. Right now, we can be somewhat naive about it. Is there anything that looks reasonable that we can try? Now, think about what would happen. So f being the gradient of little f means I really have two partial derivatives, f sub x and f sub y. So I'm looking for something, when I take the derivative of that something with respect to x, I get y. When I take the derivative of the same thing with respect to y, out comes x. Is there any function you can think of that does that? xy, okay. We have a candidate. So a candidate function. F of x comma y equals x times y. Let's check. So gradient of f would be derivative of xy with respect to x. What? Well, because we need to make sure. That's why. Oh, the variable y. Man, I keep making that mistake. Okay. The derivative of this function with respect to y. X. And does it match? Woohoo! So we're happy. Okay, so what's the punchline? We have a conservative vector field. So integration is easy in this sense. We have found the potential function. So that says that this integral along this curve y dx plus x dy is the potential function xy evaluate. So you use your bar to mean evaluation. Same thing as when you're doing integrals, because we're doing integrals. Where you start, you put that at the bottom. Where you start, you put it at the top. Like you would in Calc 1. When you plug in 1, 1, what comes out? 1. Plug in 0, 0? 0. So the answer is 1. All right. Cool. Okay. Our next problem. So here we have a curve, and I happen to have the formula written down. This is x squared plus y squared squared equals 16x squared minus 16y squared. And it looks like this figure 8. And don't worry, we can parameterize it. It won't take us that long. But we want to start here at this point, 4, 0, follow the curve as marked. And we want to end back at this point, 4, 0. Okay. Cool. What should we do? What would we like to be true? We would like to say this is a conservative function. So if we get nervous and say this doesn't look like a pleasing line integral, maybe we're not supposed to do it as a line integral. Maybe we're supposed to say, let's see if there's a conservative function in play. All right, well, how can we check? So again, we look in what's in front of the dx, what's in front of the dy. So that's x squared, y squared. And notice here, what's in front of the dx really should be the derivative of f with respect to x. It's not a coincidence that it's attached to the x. And what's in front of the dy is the derivative with respect to y. So we're looking for some function, fingers crossed, where when we take the derivative with respect to x, we get x squared. And when we take the derivative with respect to y, we get y squared. Can we think of a function that does that?
1/3 x to the third. 1/3 y cubed.
1/3 x cubed, or to the third power. 1/3 y cubed to the third. Does that work? Well, just test, right? Take the derivative with respect to x, we get x squared. Take the derivative with respect to y, we get y squared. So yes, woohoo! Now, this is great. This means that this is a conservative function, which means we can change, but we don't have to do the integral along that curve, right? We can just look at the endpoints. So this integral along the curve, x squared dx plus y squared dy is equal to this function 1/3 x cubed plus 1/3 y cubed evaluated. Where's the starting point? 4, 0. Where's the ending point? 4, 0. And what does this become? Why does it become 0? Yeah, well, you're subtracting the same quantity from itself, right? So there's a nice fact which says the integral along the curve of a conservative function is equal to 0 if C is closed. Now, there's a different way to think about this. Here we said, let's find our potential function. And we did, and then we evaluated. We subtracted. What's the other mindset we have? Because we said there's sort of two approaches. One is find a potential function. What's the other thing you can do? Bring your own curve. Can you think of another curve that starts and stops at the point 4, 0? How about just a curve that never moves? That's a curve. Is it an exciting curve? No. But not every curve has to be exciting. And so here's the curve that just stays at a point. And if you never move, what's your total going to be? 0. Now you might be saying, these are cool properties. The integral along a curve, I just need to know what happens at endpoints. The integral along a closed curve always being 0. Are these properties only for conservative functions? And the answer is yes. Conservative functions are super special. But it's not that surprising. I mean, in some sense, they're like derivatives. We like derivatives. All right. I see a question.
Okay, so I'm trying to understand why does this work? Because, like, if you just like never move, and if you go around in like the loopy-loop, it has a different length. So if we're thinking about it like it functions going up to some surface, right?
Right.
You're going a different length around. So how's the area the same as if you never move?
Well, so you have to remember, it's not necessarily just area, it's total. It's measuring something. Now, you might notice some things. Let's focus on this x squared dx for a second. What's happening in, let's say, this piece here? What's the sign?
Positive. Oh, it makes sense.
Right? X is positive, but the dx is negative. But what's happening down here?
Positive.
It's positive. And in fact, they're the opposite signs. So that the part of the curve you do here will cancel with that part. Same thing will happen down here. As I'm moving, x is negative, but x squared is positive. Dx is negative, so it's negative here, but it's positive upstairs. So it's the grand total that we're saying. It's a net total of 0.
So it's kind of more like a displacement kind of thing.
It's very much like a displacement kind of thing.
So if you wanted to like get like the total like area of like the whole thing, you'd have to throw an absolute value around it.
You'd have to go back to something like a ds. But don't worry if you're like, but I love finding areas of things. Come back on Monday. And we're going to be like, we're going to do closed curves again. And we're like, oh, it's going to be 0, right? But we're not going to do it when it's conservative. Like, no! Then we don't get fundamental theorem of calculus. Or do you? Oh, interesting things are afoot. But, that's Monday, not today. All right. So, how do you test if something's conservative? We've been making these saying, we can find things which are conservative. And essentially think of, okay, if I am conservative, I'm a collection of partial derivatives. And so I'm thinking of the first entry is the derivative with respect to x, the second entry is the derivative with respect to y. And what you can do is say, well, let's sort of go deeper down the rabbit hole. Take the derivative of the first entry with respect to y, that's f of xy, the second derivative. But one of the things we said is that for nice functions, aka every function we're going to encounter in our class, it doesn't matter which order you take two derivatives. So that's the same as taking the derivative first with respect to y, then with respect to x, which is the same as taking the second entry, taking that derivative with respect to x. So you get that m sub y equals n sub x. Now that's if you're in 2 dimensions. What about 3 dimensions? There is a test for conservative in 3D. Do you remember the test?
Divergence equals 0.
Not quite, but the curl equals 0. Take the curl across f, and out comes 0. Now, if you do take the curl across f, one of the things you'll notice is you get a couple entries here. There's a couple entries here. Do you remember what's in the last entry? Well, I mean, it's not this, because this is an equation. with an equal sign, something without an equal sign, but it is tied to this. N sub x minus m sub y. All right. So, what does that look like? Well, if this equals 0, that's the same as what you see there. Now you might be like, oh, this is it. This is when Steve said, do you remember seeing this before? This is not that yet. That's coming next week. So, all right, so that's how you test for a conservative in 3D. Essentially, you end up with, there's a series of 3 qualities to check, but it's just as fast to say, let's test the curl. Now, how do you find a potential function? Well, I used to teach a long, convoluted process, but I decided that's too long, and that's not how you really do it. So how do you do it? Well, essentially you say, if I think something has a potential, what we can do is we can search for it because we have the partial derivatives. So we have our f, which is f sub x, f sub y. This is, we think, what we look like. So when we talk about integrate the partial derivatives, we say, okay, integrate f sub x dx, integrate f sub y dy. Because what happens if you integrate the derivative with respect to x, what will this become? F, good, and dramatic pause, my pen hovering over the paper, waiting to write more down. Plus C what did you say? Yes, Y. Exactly. Now you're like, why? Yeah, why? Oh, you meant why as a question. Oh, okay, I did it again. Okay. When we integrate with respect to x, you add a constant, but you say, I'm adding a constant with respect to x. So what is constant with respect to x? Anything that doesn't involve x, which is anything which involves only y, which includes, by the way, numbers themselves. Okay, if you integrate f sub y dy, what will you get? F plus some constant function of x, right? But I don't want to use the same constant function. It might be slightly different. So when you integrate the partial derivatives, you have a really good idea what f looks like. And then you do a check for consistency. Now, the consistency says anything which involves multiple variables has to look the same. They have to agree. If you pass your check for consistency, you're conservative. Once you pass that test, you combine the pieces together and then verify. This will make more sense if we actually go through and try it out. Okay, so let's suppose we have m comma n, and I wrote something down here. I probably could have just made one up. 4x cubed plus 9x squared y squared, comma. I should have given myself more space. 16? Wow, did I really want to do a 16 there, Steve? What? I can't read my handwriting here. All right. Oh, lucky me, yes. 6. It was a 6. 6x cubed y plus 6y to the 5th. Yep, that was what I couldn't read. Okay, there's something. I claim this is a conservative. I want to find the potential. With practice, you can almost do this in your head. So we grab these two pieces and we integrate. What will we integrate this part with respect to? X, because it's in the part which corresponds to the derivative with respect to x. When I integrate with respect to x, how do I treat the y? Constant. So what does this become? X to the 4 plus 3x to the 3 y squared plus a function which depends on just y. Yes? The second part. What are we going to integrate this with respect to? Y. 6x cubed y plus 6y to the fifth dy equals 3x cubed y squared plus y to the 6 plus something that only depends on x. Now, that's step one. Consistency says, look for anything which involves both x and y. Is there anything involving both x and y? Right. Do you get the same thing in both terms? Yes? Then you're good. If the answer is no, there's problems. Either it's trying really hard to trick you, or it's not conservative. But now we're consistent, so we've passed a consistency check. So we have to combine. So we say, okay, we write down the overlap, 3x cubed y squared. Then we say, now we need stuff which only has x. Where will we find that? When we integrate with respect to x. Then you might say, well, wait, where is it down here? It is down here. Where is it? Yeah, it's hiding in the dx. Okay, and then you say, I have things which depend on y. Where do we grab those? Y to 6. Integral with respect to y. And that is again hiding in that constant function of y. And so there's our potential function. If we had time, we would verify. I think, though, there's other things we should talk about. That's it. All right, good. I found the page I'd forgotten. It was out of order. Let's do a quick problem here. Because we're almost out of time. Let C be the curve parameterized by r of t is cosine t to sine t, where t goes between 0 and pi over 2. And we're asked to find the following curve, or following integral along the curve. We have y squared arctangent x cubed y to the 6 plus y e to the x dx. And then we have 2xy arctangent x cubed y to the 6 plus e to the x dy. And for reference, I've drawn the curve. Okay. Well, what are we hoping? We hope it's conservative, because we are not going to be able to do that if it's not. Okay, so no worries, right? All we have to do is think about, let's integrate this with respect to x. All right, no worries. What's the integral of this with respect to x?
Something plus y e to the x.
Oh, I like that spirit. Something plus y e to the x. Oh, we'll even throw in a constant y for free. Yeah. Anybody know the integral of arctangent x cubed off the top of their head?
3x squared.
That was a trick question. No. You do not. But yes, you were doing a great job with the derivative. Absolutely, absolutely. Okay, so we're not going to be able to integrate that thing. So we are not going to be able to find a potential function. Does that mean it's not conservative? No. Integration is hard. Can we still know if it's conservative? Yes. Do we have a test? So, well, this is two-dimensional, so we don't need to go to curl. We'll look at these partial derivatives. We have m sub y. So let's see. We'll do this quickly. Product rule. Derivative of y squared, 2y times the second function, arctangent x cubed y to the 6, plus y squared times this derivative, which was 1, plus x cubed y to the 6th squared downstairs, then times 6 x cubed y to the 5th upstairs, plus e to the x. What is n sub x? Product rule. 2y arctangent x cubed y to the 6th plus 2xy times 1 plus x cubed y to the 6th squared. And then upstairs it'll be 3x squared y to the 6th plus an e to the x. Well, these both match. That's good. These both match. Do these match? Yes. There's 6, y to the 7th, y to the 7th, x cubed, x cubed. So, we're happy. We know it's conservative. But we can't find the potential. Oh! Is there anything we can do? BYOC. If you don't like the curve, come up with a better curve. Now, if you're coming up with the curve, what should you look for? Remember one of our mantras, 0 is our friend, except on quiz grades. But we like 0. Is there a way to move from this point to that point where we get lots and lots of zeros?
Could you move along the x-axis and then move along the y-axis?
We can split our journey into two parts. Okay, now let's talk about our journey along the x-axis. If we move along the x-axis, what's true about y? Yeah, so let's call this C1, C2. So C1 basically has something 0. So if we look, their y's are going to zero out. The y is going to zero out. This doesn't zero out, but what about dy? Zeroes out. So the integral along that segment is 0. Okay, now let's talk about this curve, C2. What does it look like? X is 0. Y looks like t. And here, 0 less than equal to t less than equal to 2. So anything with an x is going to become a lot simpler. Notice this dx. What's dx going to be? 0. So the first term completely goes away. Here, there's an x. So that goes away. So what don't we have? Well, we have this e to the x, but what is e to the x? 1. And what is dy? It's just 1, so it's dt. So this becomes the integral from 0 to 2 of 1, which is 2. And that's the answer. And you might say, we'd never asked that on a test. Except we did. So will it be on this test? I don't know. But all right, that's it for today.